everyone can share my see the screen now. Yeah, thank you very much for having me. To share with you a little bit of my experience through the journey of creating Shiny apps. First of all, I must have emphasized that I'm by no means an expert or professional in creating apps, let alone Shiny apps. But there are a lot of things that I learned through creating some of these apps, and it's a great honor to have a platform like this to talk about some of this experience. Okay, so a little bit of housekeeping. You can actually access the slide through this link, so bit.ly/shiny831. And there are some R scripts that I'm going to be using for these presentations. And you can, once you can access the slide, you can actually download from there as well. Okay. So as I should go back to the title for a little bit. So as what the title would suggest, today's presentation is going to be focusing a lot more about sort of the usability of our Shiny apps. When it comes to creating an app, we really want to make sure that our apps is responsive, is fast enough, so that people don't, click a button and wait for, 10 seconds for another screen to come up or something like that. And oftentimes this involves good design of, your workflow behind what's going on in your, server side of your Shiny apps. But it also involves a lot of efficient coding as well. That is kind of like what I'm going to walk you through some of my experience in creating some of these things. But first, I will demonstrate one of the Shiny apps, sort of quite elaborate ones that I have done as part of my PhD research. And this is specifically on, looking at the relationship between travel time to health facilities and malaria. So malaria is, still a devastating disease affecting hundreds of millions of people around the world. A lot of us might not have heard much or worried much about malaria, but for people in the sub-Saharan Africa, for example, these are where malaria is still, affecting the economies and livelihoods of people. For this project, I work with my PhD advisor, Dennis Valley, and my former lab mate, Justin Miller, and also our Ghanaian collaborators. Focusing on a district that is in the northern side of Ghana. It's called Bumpuruguyunyo district, pretty small districts up here at the border of Togo. And what you're looking at right here is results of a survey done back in 2010 to 2013. You're looking at the malaria prevalence of the district here. Ooh, okay. Is there a way to get rid of this? Okay, come down here. Okay, what you're looking at is the malaria prevalence here. Specifically, the survey was focusing on the children under 5. This is the age group that is most affected by malaria compared to like the older children and adults. So as you can see from the map here, even within the district itself, you can see that the southern regions of the district is, you experience very high malaria prevalence up to like 80% or 90% down here. And then in northern area, you get to much lower prevalence, like 10%, for example, 20%. There's 2 urban centers in this district. It's called Napanduri here and Bumpurugu. So based on the data that we collected and based on the statistical analysis that we've done, it comes up that one of the very strong predictor of malaria prevalence here is actually distance or travel time to health facilities. When we say this statement out loud, it really makes sense that, well, if that's the case, why not we build a bunch more, health facilities all over the district, and this would probably help to bring down the malaria prevalence. And there's some sort of a little bit of causal relationship there, because we know that early treatment and diagnosis of malaria can actually stop the malaria transmission as well. So that is the whole idea of this app. We want to let people to explore what happens if you add more health facilities onto the map. What does that mean to malaria prevalence or malaria incidence? As you can see from the metric here, you can choose to see malaria incidence instead of malaria prevalence, or what does it mean in terms of travel time to the nearest health facilities. The whole idea of the app is that when people interact with the map and trying to add more health facilities, they get the idea that what really are the numbers that our data tell us, right? And whether or not it makes sense. And if it makes sense to us, where is the best place should we place our new health facilities? Okay. So that is the whole idea, and what you are seeing here, there are like 8 health facilities that exist in the district. 5 of them are in blue colors. They are the health centers, and 3 of them are in red. They are the sort of community-based kind of like mobile health post. Okay, so lots and lots of things that you can look at. Again, if you look at travel time, for example, of the map, you can see that in the southern regions of the district, the travel time to nearest health facilities tends to be large. So people have less access to healthcare in the southern regions of the district, for example. Okay, so what we ask the user to do is, well, you can choose where you want to add a new health facility. Say, for example, I look at this map, I say that, well, these regions, people are, have less access to healthcare. Let's add a health facility here. So click on it, there's a red dot appear here, and I can say add facilities here. Okay, once I added the facilities, I say update the predictions, and let me see what does it mean after I add these health facilities here. Okay, once I added it, perhaps it's easier to look at the difference from the baseline because we can now see what has changed. So right now we are looking at travel time. You can see that by adding a health facilities here, we improve the travel time in the close vicinities of these health facilities. It all makes sense, right? But you can see that the impact is kind of localized. The predicted impact, I must add, is kind of localized here. And you can also look at prevalence. Again, the changes is pretty much localized to what you see here. Okay, so again, incidence is even lower, it seems like. Okay, so and then over here, this would show the district-wide prevalence, district-wide incidence, and district-wide travel time per person. And you can see that the reductions is actually very, very small for adding the health facilities here. So it kind of is a strange, right? Apparently I have improved, I have added health facilities onto a spot where the travel time was high. So what happened here? That's because there are a lot of interactions with the underlying populations. So there were simply more people living in the northern area of the district compared to the southern area of the district. So when you improve the travel time, you improve the travel time for maybe like a small portions of the people. And as a result, you don't see a big impact when it comes to a district-wide kind of metrics. So let's say now that I have this mental model, I go back and say, okay, let's choose a spot that is near the roads. It's not very clear here, but it's kind of, you can see that there are 3 roads leading to this particular spot called Yunyo. It's sort of a very small town, rural towns here. Let's add a health facilities here. Okay, so once I add it, again, I click update predictions. Not too obvious, but I can look at the difference and I can see that the improvements in terms of prevalence is a whole lot more. Like you can see that the reach of these new health facilities is a lot more compared to the spot just now. And you can also see that travel time is also, improved just by marginally for a lot of regions around this area. Basically, you see that the impact is area is slightly larger. When it comes to district-wide metric, again, you can see that the numbers, the reductions from the baseline tends to be larger as well, just simply because we choose a spot where the populations is higher. Okay, so that is very much the sort of like the first functionalities of the app. You get to choose and pick a spot and choose and see what it means in terms of your actions of adding a new health facilities. These are all based on the data that is generated back in 2010 to 2013. There's an underlying model here. We are using a generalized additive model with distance and some other covariates driving the predictions that you see here. Okay, so let's say you're done, adding new health facilities and playing around with this part of the app. You can also ask the app to optimize the locations for you. Choose a criteria that you want. For example, in this case, I want to reduce the district-wide prevalence of children under 5 as much as possible. And say, for example, I want to add 3 new health facilities. I can click the optimize button here. And it would tell me in purple, these are the 3 locations that you should add the new health facilities. And these are the performance in terms of district-wide prevalence, incidence, and travel time based on the 3 new health facilities that are optimized. Okay, so these sort of give people an idea. Well, if you were to, minimize some of these metrics that you want, where are the locations that you want to add? Furthermore, this also actually give a little bit of idea of how much you can actually achieve by just utilizing these correlations that we have, which is to say actually is not a lot, right? Reductions of 0.6% prevalence compared to a baseline prevalence of 40%. Although in terms of travel time, you do reduce by quite substantially. And that is also a good idea because you want to bring healthcare to the people so that people did not need to travel that much more time to the health facilities. So it's not essentially a bad thing as well. But the idea is that if you were to fight malaria by building new health facilities, you really want to think that the return is probably not as much as what a blanket statements of, well, there's malaria prevalence where travel time to health facilities is significant, is a strong predictors of malaria prevalence. But when it comes to actually using pen and paper and draw things out, in this case, mouse and keyboards, you do realize that the effect is not as strong as you would think. So that is very much the app that I'm showcasing here. But the idea is that when I designed this app from the very beginning to what you see here, a lot of consideration is on the speed of calculations, whether or not my apps are responsive enough. And I come to the point where I think that, hey, you know what, my app has been doing a pretty good job, I must say, in doing all these predictions on top of, letting people interact with some of these elements. And I can keep adding new health facilities, update predictions, and these usually take, less than a second to get a new visualizations. There's very much what's in my mind when I design a relatively complicated, elaborate kind of apps. Is all about the usability of my apps. And I really want to make sure that my app can process things quickly so that people won't get bored or people won't get turned off by it. And so for the next, maybe half an hour or so, I'm going to walk you through some of the considerations that I bring when it comes to creating a Shiny app that I feel like is responsive enough for the user, such that the user experience is there. Again, there are a lot of thoughts behind user experience as a whole, and usability is definitely only one part of user experience. And by no means I'm not an expert on user experience, but these are something that I learned by developing Shiny apps. Before I go into what's kind of promised in my title, that is like improving speed of Shiny apps by pre-computing models, I really want to give a lot of shout outs on coding efficiently. Oftentimes we think that, we are not professional R coder, we are not like computing scientists. Let's not think about, optimizing our code or efficiency in coding. But for me, large part of my career, large part of my PhD research has been about, writing code and using the code to achieve something. And I feel like for many of us, in the same boat, it really is something that we should be investing our time to improve our code efficiency. This is a great book. I've gone through quite a large part of it. There are really lots and lots of good advice out of the book. You can check it out, click the link. I think there are like all sorts of efficient way from start to finish. But for these presentations, I want to focus on a number of points that I find myself very, very useful for myself, and I hope to you as well. The good old story about vectorization or loop. If you find yourself doing some relatively simple tasks that is done using for loop, sometimes you really want to question yourself, is there a vectorization equivalence of the methods that you're using? And oftentimes there are a lot of native functions, or someone has written the functions out there that are already very optimized and already utilizing vectorization methods. And sometimes we want to leverage on some of these functions out there. There's a point about, so if you look at your RStudio, there's a button called Profile. I'm not sure if you have ever used that, but this has been, I've been using profilers lots and lots of time in my journey of not just writing R code, but also writing Shiny apps to really gain insights about which part of my code is taking a very long time to execute. I'm also going to briefly demonstrate it later to you. And finally, as much as like sometimes we want to stick to using base R package, tidyverse and data table package, can be really, really important and useful for our R coding in terms of saving times as well. And I'm also gonna demonstrate it to you in the 3 demos that in the following slides. So I don't really have good examples on like how exactly to make a good vectorizations and whatnot, but I'm gonna tell you a story of questions that always come up in my mind. I've used R for quite a number of years, but one thing that I still couldn't find out until last year is how exactly to calculate moving average in a very elegant way. You can actually download the R script here. I'm gonna jump over to the R script to tell this part of the story. Demo1.r. Okay, so for this script, I rely on dplyr, and I also rely on this package called microbenchmark. It is a very helpful package to really learn about execution speed of my code. Okay, especially when the code is running too quickly for you to capture the running time sometimes. Okay, so I start out with generating some random time series. So set some seed and use sort of like a AR model to generate a random time series. And you see a random time series here. Imagine from 0 to 1,000 days, you're measuring some values on the y-axis that goes from starting from 0 all the way up to maybe a little bit more than 1,000. As I say, for the longest time, I haven't known what are the, like a best way to calculate my moving average. And it turns out that I have to, create a functions and write a for loop to make, calculate moving average like this. Okay, and then last year when I was involved in a lot of COVID-19 kind of visualizations, that's when I, really dig out from the Google verse, from the internet, and find out that there's actually a pretty obscure sounding function. It's called filter that comes with the base R package, and because it always interferes with dplyr package, which also have a filter functions, so I would add a prefix here, stats ::. It's not very intuitive, but this is how exactly you calculate a 7-day moving average, for example. So in this micro benchmark functions, I compare the first method I put in the first place with the second methods I put in the second place here to calculate moving average. So I run micro benchmark. Obviously, I haven't run everything. So, okay, yeah. And I think if there's a way for me to, okay, yeah, enlarge. Okay, does it improve my, okay. So again, you want to use micro benchmark, especially because your code execution speed is very fast. But in this case, you can see that the first method using a for loop, the mean time of executions is about 14 milliseconds. Milliseconds is 10 to the power of -3. So it's like 0.014 seconds compared to the so-called native way of calculating moving average. That takes almost only 1 in 100 or 1/50th time of the time that we use for when we were to use a for loop. So the idea here is that the stats filter package, the function utilizes vectorizations behind the scene, and it also pass a lot of these calculations to the foundations of R, which is actually C language. Okay, it passed a lot of the calculations to C language and let C do the job. And C does this kind of job much, much, much better compared to R. And so the package does all this for you. No, sorry, not the package. The function does all these things for you. And therefore, you can see a much better calculation speed compared to using like a handwritten for loop way of doing things. And just so, just to make sure that I'm doing it right, it seems like I'm calculating my moving average right in this case. Okay, so that is just a little bit of for a lot of us, I think we are all aware of like the power of vectorizations and native functions compared to using for loop. But and if that's the case, it's a good refresher to remind yourself using a for loop sometimes can take like a lot more time compared to using some of these native way of doing things. Now, the second demo is a lot more closer to what you see in my Shiny app just now. Okay. Sometimes we rely on functions that's developed by someone else that does not support vectorizations. And that's very unfortunate in my case. So remember that I showed you the app that I have just now. There's an incidence, right? So we actually don't collect any data on incidents. So this survey done back in 2010 to 2013, there was no incidence data. And in fact, incidence data is notoriously difficult to collect because we need to go to the health facilities and they don't always make record until recent years, for example. So we rely on Malaria Alice Project, which is a group that was based in University of Oxford. Now I think is in University of Western Australia. They were the one who make some sort of a statistical model to correlate the relationship between malaria prevalence and incidence. Okay, prevalence and incidence relationship is not linear. And as a result, we need some sort of conversion equations and formula that is sort of like I think it's a polynomial to convert the relationship between malaria prevalence to malaria incidence. But before I can even do that, I need to do another conversions. In this case, malaria parasite prevalence that we collected on the ground is actually from children of 0 to 5 years old. But the equations that the Malaria Atlas project came up with was actually from 2 years old to 9 years old. They convert malaria prevalence of 2 years old to 9 years old to incidence. So we need to first convert our malaria parasite prevalence from 0 to 5 years old to 2 to 9 years old. And thankfully, again, from the same team, back in 2007, they actually created a package to do this job for us. And I'm going to move over to the R script, and you can actually download the R script. I think Jody has shared the link in the chat as well. Okay, so this is the second demo and the R script. Okay. So first of all, I rely on the package, and R has over the years has helped us install package out of GitHub, and this is how you would install the package through the team's GitHub. And then I have already installed the package, so I can just run library hstand. So in these demonstrations, and it's very much what happened in my app as well. Imagine that I have a 100 pixel and 100 pixels times 100 pixels area. Each of these pixels has a prevalence value. So in total, I have 10,000 prevalence values that I need to convert first from 0 to 5 years old to 2 to 9 years old. And then after that, from that step, I can convert it to incidence. Okay, so let's create some random numbers. R unif, from 0 to 1, right? Prevalence is a number that is from 0 to 1. So we create 10,000 values here. And so here I'm gonna run a profiler just to let you have a taste if you haven't seen what a profiler looks like. I'm gonna choose the first way and the second way that I'm comparing, and I put into my profiler. What I do is I can click profile down, and you can see that there's a profile selected lines here, and I will click it. It's gonna take a while, and here's what I'm gonna explain to you. What are the both ways? So the first way is to put in that 10,000 values directly into the convert prevalence function that is provided to us by hstem package. Okay, and here I need to specify that the values that I put in is actually prevalence of 0 to 5 years old. Okay, the results of the profile one has come out, but I'm just gonna explain through the code first. Okay, for the second, for the first way, I put the 10,000 value into the function directly. But I know that if I were to run in my console, convert prevalence, I know that this function that is created by this malaria adders project group, they rely heavily on for loop. Okay, so they would make the calculations one by one, first value, second value, third value, all the way down to 10,000th value. And this is gonna take a lot of time for me. Okay, and we can look at the profiler later to see how long it takes. So I'm like, no, I'm not gonna let this happen. I'm not gonna take 10 seconds to let my user wait for 10 seconds just for this conversion to be done. Okay, here is another way that I propose. Because the prevalence to incidence conversions is actually one-to-one and monotonically increasing, I use this to my advantage. So instead of running 10,000 value, I say convert prevalence value of 1001. And this 1001 value is very specifically 0, 0.01, 001, 0.002, 0.003, all the way down to 0.999 and 1. Okay, so this is a sequence of values. So once I calculated this value, and it's called pre-calc, I can use the quantile functions, and I can put in my R, the vectors, and I can pull values based on these pre-calc vector. This is all thanks to the fact that the conversion is actually monotonically increasing. Okay, and because of that, I only need to put in 1001 value into this convert prevalence function. And you can see the result in the profiler. So the profiler is great because profiler let us know line by line what are the time taken to execute this particular line. Okay, the graphic down here usually don't make a whole lot of sense, but the graphic up here is very, very useful. So what the profiler tell me here is that for my first way of executions, it takes 17,000 milliseconds, which means 17 seconds. Okay, to fully convert the 10,000 value. But for my second way, it takes 1700 milliseconds, which means 1.7 seconds to run this first line of code. And then to run this second line of code using quantile, it takes 10 milliseconds. So in total, I achieve the same task only in 1/10 of the time if I were to just blindly use the convert prevalence function that is provided to me by this group back in Oxford. Okay. And in fact, in the profiler, you can actually also look into data panel, and you can actually look specifically into convert prevalence function, which are the steps that is actually taking a lot of your time. For example, invert PF. Sometimes there are more information here if you know what's going on with the invert PF sections of the function. And these particular sections really helped me a lot in my journey in terms of coding R. Okay, so just to close this section out, I want to just to show you that my conversions for both way, they were actually more or less exactly identical. Just so that you know I'm not cheating you by using my second way here. Okay, so that is this very much relevant to what I'm doing in my Shiny apps. The third demonstration is also kind of relevant to a lot of my other Shiny apps that I don't get to present to you today. Is the idea that sometimes we rely on some sort of external source to read in a large tables, a big CSV table. Okay, and oftentimes when these kind of things happen, so for example, your Shiny app at the back end, you're reading in hundreds of thousands of rows of CSV, and then you do some data manipulations before you turn it into a visualizations, then very much you want to use packages like Tidyverse and data table to do these kind of manipulations. And the R scripts that's supporting these demonstrations is here. And I'm gonna go over to the code in my RStudio. So in this demonstration, I'm going to show you sort of the comparison of the Tidyverse packages. So Tidyverse packages include dplyr that we know of, tidyr, reader is another package that comes with Tidyverse. Reader, obviously from the name you can see that is how you use it to read certain data table, for example, CSV. Data table package is sort of like an MVP package when it comes to big data kind of analysis, and then micro benchmark. Okay, so the first step of my sort of demonstrations is that I need to be able to generate fake data frame. In this case, I specify the number of columns and the number of rows that I want to generate, and then it's going to generate a fake data frame for me that is full of numbers. I'm going to create a result table. In this case, I'm going to run it first because it's going to take some time before I explain what's going on in this chunk of code. Okay, in this chunk of code, basically I asked the three functions in base R. That is the read.csv. In reader package, that's a read_CSV. And in data.table, I'm using the function called fread. So the three functions in the three packages, I asked them to read, first of all, a CSV that has 10 rows of data. And then increasingly, I asked them to read 100 rows of data, and then 1,000 rows of data, and then 10,000 rows of data, and then 100,000 rows of data. And in each of these steps, I record the number of time, the amount of time that is used to execute this function. So system.time allows me to do that, and I record them into my empty data frame there. Okay, great. I'm done now. Just in time for me to plot the results. And we can also look at the table here. So you can see from the data, from the plots here, by 10 to the power 4, which means 10,000 rows of CSV, you can see that the performance of base R package start to be, really not good. And then by 100,000 rows, you see that time taken to read the CSV went up to about 50 seconds. Your mileage may vary because I'm using an 8-year-old computer right now. It does seem to take a lot more if you were compared to using a much faster computer. For reader package, you can see that up to 10,000 rows, the performance is still not bad, but when it comes to 100,000 rows, the performance tends to deteriorate. But when it comes to data.table function, that is fread, you can see that the performance even up to 10 to the power 5 rows is still pretty good. It takes about 0.34 seconds to load that amount of CSV into our system. But really, sometimes if we didn't need to rely on some sort of external sources of data CSV file, for example, we can actually store our data frame, big tables, for example, into this format called RDS. So RDS is sort of like a binary files that is specific to R that is used to store R objects. Okay, and you can use an write RDS functions to write the data frame into this file called, for example, temp.rds. Okay, if you sort of calculate the number of time that is that it takes to read RDS, you can see that it takes only about 0.11 seconds to read this RDS format. So whenever it's possible, you should also try to use the advantage of RDS files. Okay, just a quick demonstrations of filtering. When it comes to filtering, I am comparing 4 types of filtering. The first one is base R filtering. The second one is use dplyr filter functions. The third one is I convert my data frame to a data table object first before I use the data table way of filtering. And the fourth one is I use the data table object that comes with the data table package and to do the filtering. It's gonna take a while as well. Which means I get to have a breather before we talk about it. But you can also see here the performance of the packages compared to the base R package. In this case, you don't get that much of a performance improvement compared to the read CSV, for example, but you are still looking at, for example, mean time of running dplyr filter functions, or the mean time of using a data table way of filtering is still about kind of 1/3 to 1/4 of what you would be using comparing to a base R package. So if your Shiny apps is using a lot of these kind of manipulations behind the scenes, you really want to consider using tidyverse or data table to your advantage. Okay, so these are the 3 points in terms of efficient coding that I feel very strongly about, that I have been applying to a lot of my Shiny apps that I have created. I hope these small demonstrations is useful for you when it comes to coding efficiently in your Shiny app or just general R coding. The next part is very much related to the second demo that I showed you just now. We pre-calculate things. We store, in this case, so when you store this particular pre_calc, for example, you can keep on using it for over and over again until my user is tired of using my Shiny apps, for example. Right, so you do one-time calculations and you can keep on using them. And that is the philosophy in a lot of our Shiny app development. It is extremely helpful for us to write out our workflow and then analyze which part of our workflow can actually be stored away or can actually be pre-calculated if it's taking too much of our time. So just to look back at the Health Facilities app that I showed you just now, here are, for example, for the first functionalities, here are the workflows that I sort of, in my mental model, sort of I created this based on what I think I want to add onto my app. So first of all, I load the data and then I feed the GAM model. Both of these are really, really fast. And then I ask user for new coordinates. And then I calculate new travel time based on new coordinates. This is the part where I'm not too sure because it could be that like it's going to take quite a little bit of my time. But you will see that it turns out that it turns out that the calculations was actually pretty fast. So I'm kind of lucky in the way that, these calculations is not very long. And then finally, I produce a new predictions using the GAM. So it turns out that GAM, GLM, or some of the linear models, when you use the predict functions that they provide, these are actually just a bunch of matrix computations behind it. And so these functions are generally very, very fast, even when you have like tens of thousands of predictions that you want to do. So in my Shiny app, I didn't think that loading data and feeding GAM model makes sense in my Shiny app. So what I did was I stored the GAM model away. And then when I need it, I will pop the pre-fitted GAM into my Shiny app and use it for predictions in the later part of the workflow. And this is sort of like the workflow that I decide for my Shiny app. Just to show you how you can store your models, just in case you not sure how to do it. For example, I use MGCV to fit my GAM model. And this is just creating a bunch of fake data, and then I fit the model using GAM. And in this GAM, I have two-dimensional splines here. And my GAM model is fitted. And then what I did was I use a save function, and I say I want to save this object called mod, and save it into a file called gam_mod.rda. I'm not sure what's the significance of .rda, the extension itself. I'm pretty sure you can use other random extension, but when I learned these functions, someone else uses .rda, which seems to be standing for .r data. And that's what I use. I save it away. So now in my environments, there is a gam_mod.rda file. And then when I need it, I can use a load function and I load this particular file. And then when I run mod, you can see that the mod is now in my system. So this is a great way of storing your model away and then pop it back up when you need it. Okay. We also have the optimization functionalities in the health facility app, and again, this is sort of the workflow of my optimizations functionalities, and there's a particular steps that takes forever, right? Spatial optimize, we use sort of like a genetic algorithms to do our spatial optimization to find out which is the best spot to place these new health facilities. This takes an extremely long time. And so what I did was I realized that I can pre-optimize and store these coordinates into a CSV file. So when I need it, I would just pull these pre-optimized coordinates and show it to my users. So this obviously turned 30 minutes feeding time to 0 seconds, literally. And if you want to have a look, this is kind of like how I organize that CSV file. So this is the number of health facilities. When my users say they want 3 health facilities, these are the 3 longitude and latitude that I'm gonna display to my user. And then this with the metrics as well. You can choose the different metrics and they would have a different corresponding longitude and latitude to display. So in some way, I'm turning my Shiny app from a big calculator to more or less a big, not so big calculators and more like a visualizer here. And I think this is extremely useful for many of us who often have to use things like optimizations, or sometimes certain things that we know that is sort of going to be staying stagnant. This is a very helpful way of designing our Shiny app around it. I'm not sure, are we really very on time here, or would you spare a few more minutes?
I think go ahead. If people need to leave, feel free to leave, but we're recording and we can make it available for people that need to leave. So, but keep going.
Cool, yeah. Just gonna address a little bit about the issues. Sometimes though, I say that like predictions from GAM is very fast, so we can just embed the function, the model into our Shiny apps. But sometimes though, our Shiny our model can be very complicated, and that predictions out of the model directly isn't that simple and fast. And this is a work that I've done with another group in University of Florida. They came up with a very sophisticated and complicated model to model the distributions of Aedes aegypti and Aedes albopictus. These are 2 types of mosquitoes that are known to transmit Aedes, chikungunya, and I think Zika virus as well. And they use a bunch of environmental covariates, and they also come up with a zero-inflated negative binomial model with site and county level kind of random effects. So a very complicated model, and more so that they actually rely on a package called GLMM-TMB to fit this model. And the problem is that fitting the model takes hours. And then the worst part is if we were to use the predict function that comes out from the GLMM-TMB package, there were a lot of calculations behind this to make extremely accurate, model accurate kind of predictions when it comes to uncertainty as well. And this takes extremely long time. So in that case, this is really tricky for us. But in this case, sometimes you want to realize that model is essentially a bunch of estimated parameters. And sometimes what we really want to do is to be able to dig deep into the model and to pull the parameters out from the GLMN object, for example, and calculate the predictions ourselves. This requires a little bit of understanding of the statistics behind, but I think it is extremely useful in this case because we are turning 1 hour prediction time to, again, essentially 0 seconds, so 1 second kind of calculations. This app is still under development, so I'm just going to be able to show you briefly what has been done to let you have a feel about what happened when you pull these estimated parameters out and to actually use it for calculations and calculate your predictions yourself instead of relying on the package inbuilt kind of function. This turns out to take a long time. Let's hope that it doesn't. Well, seems like someone somewhere is not very happy with me. Okay, Shiny Apps is not happy with me. I guess I will not be able to show you, but the idea is the same, that we have some sort of a control panel that allows people to change their county, change their environmental covariates, and they get to see the predictions almost immediately. And that would be some sort of, this I think is the kind of workflow that I very much recommend for people who are, for example, using very complicated model. For example, sometimes we feed it some sort of like a multi-level hierarchical models, and it often involves us storing all these like a posterior samples of the estimated parameters. And when it comes to the Shiny apps, we use these pre-stored, pre-fitted kind of posterior samples and just make multiplications, matrix computations behind the scene. These are very, when it comes to matrix computations, these are calculations are very fast and generally don't take us a whole lot of time. So that's very much what I have to show you about today's topic, and I will close out my presentation with some final random tips that are very close to me. I have been doing a lot of geospatial kind of visualizations, and I find that SF is generally faster than SP when it comes to shape files and whatnot, but sometimes we still rely on SP because it works better together with the rasters. High quality shape files can sometimes take much longer time to render in plots and leaflets. I didn't get to show you the app that I wanted to show you just now, but that would be an example where a Florida map shape files turns out to be too detailed, and I had to downgrade my shape files using, for example, gsimplify functions from the Arjus package. And finally, this gave me a heart attack a few hours before this presentation. Something wrong with my code in my Shiny apps that I show you, the health facility Shiny apps. It turns out that it's because filter function, for example, select functions, there are multiple packages that has the same functions. And sometimes I got no idea which functions are you referring to. So do remember to sometimes shockproof your code, add prefix of dplyr, for example, in front of your filter and in front of select functions. That's very much for the presentation. Thank you very much. And yeah. here are some of my contact details. Feel free to give me questions, comments, suggestions, and if there's any questions, I would like to hear it.
All right, thanks, Ben, for that presentation. So there's at least a few questions so far. The first one being, I just more of a comment that there's also the role apply function that can also be used to calculate moving averages.
Yeah.
The first question is there a way to use the profiling tool to measure speed of functions in Shiny? So for example, like quantifying reactive changes to a map or a graph or something like that.
Oh, I'm not aware of using a profiler directly with Shiny apps. So I think it was last week's presentation. Like there are ways for people to test their Shiny apps based on a certain preset inputs, and I think that would be the best way for you to profile what happened if the user put this input and what are the time take to profile those codes. Yeah, I'm not aware of any great way to directly using profiler with Shiny apps.
Okay, and another question asks, what's the difference between an .r data file and a .rds or RDA file?
Yeah, that is a very good question. I definitely asked that myself before, but I didn't quite find out my answer. My gut feeling is that RDS and RDA, they both work the same way. So you most likely can write the model into RDS without problems. Yeah, so that is as much as I can say. But yeah, that's as much as I can say about it.
Okay. And another question asks if you know if there's a speed difference between plotting methods for ggplot or BaseR, other different plotting methods.
Not so much. I feel like I haven't seen a particular difference between ggplot and BaseR plot. But I do want to say that there are certain things that you do that can take longer to plot in one plot compared to another plot. For example, there are certain small things like the choice of colors or the choice of the size of your dots. Those actually make a difference.
Okay, well, I think those are all the questions. There's one more. One person posted a link that there's a profiler for profviz, that function that works with Shiny, although it hasn't really been tested that much, or they haven't tested it much.
Oh, great. Yeah, that's great to know. Okay. Yeah. Okay. Is there like a Shiny? No, maybe not. Oh yeah, profiling a Shiny app. Oh, that's great. Yeah. Yeah, that could be one way to, yeah, well, yeah, right. So you actually have like a run examples that you can profit through it. Yeah, that's right. So I think it was last week's presentations or 2 weeks ago that, yeah, you can use a run example to sort of test run your Shiny app. And then you can add a sort of like a wrapper out of the profits. Yeah. Thank you so much for the comments.